Newton's method is a pretty useful tool in calculus. It can be used to basically estimate roots of functions without actually having to solve for the roots of the function, which is pretty nice sometimes. But what you may be missing out on is what are we actually doing when we do Newton's method? I think it's massively helpful to understand kind of graphically what this actually looks like and what it actually means rather than just iterating through a formula. So in this video, I wanted to show you an example of how to apply Newton's method, the formula, but also what it actually means and give you a visual representation of what we're actually doing. Because I know I find that kind of stuff super helpful. And this actually came from one of my weekly live streams that I've been doing every Monday night at 5 Pacific, 8 Eastern. Be sure to subscribe to my channel and turn on all notifications with that little bell icon down there so you're notified when I'm going live each week, and hope to see you there. But anyways, let's go ahead and jump on into this example and let's learn about Newton's method. We're going to use Newton's method with an initial approximation of x1 equals -1 to find x2. The second approximation to the root of the equation x cubed plus x plus 3 equals 0. Then we're going to explain how this works by graphing the function and its tangent line at the point -1, 1. So really this problem is kind of a, I don't want to say like easy or basic, but it's not as in-depth of an example as you may run into with applying Newton's method. And the reason for that is, as you can see, we have an initial approximation of x1, and all we need to do is find the second approximation. So a lot of times with these Newton's method problems, what you're going to do is apply Newton's method several times, maybe 5, 10 times. Probably not 10, but more than once often, usually. But really, to do this, the point of Newton's method you want to keep in mind is really all we're doing with Newton's method is trying to find solutions to the equation some function equals 0, or in other words, finding roots or the root of an equation. Well, the root of an equation basically just means if we have some equation like this equaling to 0, we want to think about the function, which is just all the other stuff that's equal to 0. So in this case, x cubed plus x plus 3. This is going to be the function f of x that we're going to basically use in the Newton method formula to find our next approximation of the root. Well, to do that, there's really just a Newton's method formula that we're going to use. So this is it. We're just basically want to keep in mind to find the n+1 estimate of the root, we just take our previous estimate, the x sub n estimate, minus whatever we get from plugging that estimate into our function over whatever we get from plugging that estimate into the derivative of our function. So that's really what we're going to be doing here. So let's think about these different pieces of this equation and what they're saying. So to find our x sub n+1, in this case, this problem tells us we're trying to find our second approximation. So we're trying to find x sub 2. All we should need to do is take our previous estimate, our first estimate in this case, minus whatever we get from plugging that first estimate into our function, over whatever we get from plugging that first estimate into the derivative of our function. So to find our second approximation, we can do it just using our first approximation, which is x sub 1 equals -1. They gave us that right here. And the function that we got from this equation right here. So these two pieces can be used to estimate our second approximation, or to figure out our second approximation. So in this case, what that's going to be is basically just replacing x sub 1 with -1, which means x of 2 equals -1 minus f of -1 over f prime of -1. So we are going to need to find f prime, first of all, which we should be able to do using just our original function f of x here. So we're just going to find the derivative of this function, which we can do just using the power rule. So the power rule says we'll bring our power down in front, bring our 3 down in front, leave x as the base, lower our power by 1. So 3 minus 1 is 2. The derivative of x is just 1, and then the derivative of a constant is 0. So our f prime is going to be 3x squared plus 1. So now to figure out kind of our next step here is to figure out the f of -1, which is going to be whatever we get from just plugging -1 into our function f here. So f of -1 is just going to be -1 cubed plus -1 plus 3. -1 cubed is -1, plus -1 is -1, plus 3 is 1. So f of -1 is 1. And then f prime of -1, we're just going to plug -1 into f prime of x, which we found right here. So we're going to get 3 times -1 squared plus 1, which is -1 squared is 1, times 3 is 3, plus 1 is 4. So this is going to be 4, f prime of -1. So simplifying this, we're just going to get -1 minus 1/4, which, to add fractions, we would need to make sure to get a like denominator. So -1 is the same as -4 over 4, and then -1 over 4, which gives us -5 over 4. So basically our second approximation of the root of this equation is just -5/4. So now what we need to do is consider why this works, or how this looks on a graph, essentially. So that's what I have kind of jotted down here. Now, this is just kind of a rough sketch. It's certainly not a perfect drawing of what this function looks like. And in fact, I probably should have used a little bit different scaling, because if you kind of scale your y-axis a little bit further out rather than going at units of 1, if we consider like going up to 10 or something, but then keep our x-axis going in units of 1. So 1, 2, 3, like that. We get something a little bit more interesting here, which basically would be kind of more like that. Actually, that's not quite right. More like that. You might be able to see it a little bit better if you kind of zoomed out on that. But anyways, what we have here basically is we have our y-intercept of 3. It does have kind of this S-shaped curve to it. And we do know that it goes through the point -1, 1, like the problem told us to consider. We want to look at the function and its tangent line at -1, 1. Well, if we plug in -1 into our function here, we get +1. So we know that our function goes through that point, -1, 1. And therefore, we're looking at the tangent line of this function that goes through that point. So you can see, looking at this graph here, our function, which we just figured out our x2 estimate of using Newton's method to approximate this root. So graphically, where this root lies is right here. It's where our function intersects with the x-axis. Well, we just figured out, using our first estimate of x equals -1, which is right here, our first estimate at x equals -1, graphically what Newton's method is doing is it's essentially drawing a tangent line to your function from your prior estimate, and then extending that tangent line down to the x-axis. And then where that intersects is what you use as your second estimate. So basically, if we look at this tangent line here, it intersects with our x-axis of our function at the second estimate we got, which was -5/4. So basically, we can see that this intersection right here of this green tangent line with our white x-axis here is -5/4. Now, if we were to then consider our next estimate, what we would do is go from this spot here on our x-axis down to our function, and then do the same thing again there. We would draw a new tangent line from this point down here and see where that intersects with our x-axis. And it's kind of hard to see here without like really zooming in, which I'm not sure I can do here. I don't think I can. It's not really a good way to zoom, but if you were to kind of graph this using some graphing software or a graphing calculator, you could definitely zoom in. And if you graph your next tangent line from this point here at -5/4, you would then see that your tangent line would intersect with the x-axis much closer to where your function does. And that's kind of the point, is that each time you iterate through this this Newton's method, you're just getting a little bit closer to the estimate of the root that you were the time before that. So that's kind of the idea there with that. Well, I hope you found this video helpful. If you did, please be sure to hit that thumbs up button, hit that like button down below. It's a huge help so I can keep making more videos like this. And be sure to check out my Calculus 1 study guide. It's free, it's available for instant download. There's a link down in the description where you can check that out. And if you want to keep learning about other topics covered in that study guide, I have made several other videos going over different topics that are on there. So be sure to check those out over there, and see you next time.